And I appreciate you sending it in. I really appreciate that. Did you get to do the hacker rank? Did you submit that, or just you write the code?
No, I didn't get to do the hacker rank. I tried using this one, and I don't think it worked.
Yeah, it's always a
Um,
little tricky, especially if you're
yeah.
putting in yeah, if you put in, yeah, weird. Yeah, but it looks good though. So, yeah, because the problem is with this hacker rank, and I think I brought it up last week, they provide the code for you somewhat, but it's so rigid that if you put it in, even if it works in the notebook, it won't work here, which is kind of a pain in the booty. Doesn't matter. It's just a cool way to be able to join the community, so it's not mandatory. Not for this class. I know with the other ones that I'm doing. So what we're doing here is we're basically defining, we're going to be given two complex numbers, and you have to print the result of the addition, subtraction, multiplication, division, and modulus operations. Again, a bunch of math that really doesn't really matter too much, but what's cool about this is we're defining a class and creating functions. And so these functions some of them are already predefined, add, self, and then basically being able to add those things in. So, did you want to say anything about how hard you felt this was and what you were doing with this, Stephanie?
Um, so I had to understand the question first and see what you wanted to get out of it, and then kind of understand like the code that they gave first, like
Yes.
their template. And then I kind of just like looked around Google, looked at the ways that other people did it, and see which one could work or which one made the most sense in my head.
Cool. And that's exactly the way I tell people to do is just go Google it first. Someone's run into this problem before, or they've already kind of done this. And so what you did, which I think is kind of cool, is you basically created a function here to go through when they input these numbers. You're basically doing the input, doing a split of those, and then you're doing the complex, and then you're basically printing out all of the different examples of this in one big go, which I think is kind of cool. You're basically doing those numbers, passing them through, and then you just do the complex. You do the add, the subtraction, the multiplication, the modulus, all in one shot. Correct?
Yes.
Yeah. Gotcha. Cool. That's awesome. Well, with that being said, I don't want to go too more into this because now we are going to get busy, and I'm going to go deep. And I like this. We're going to be doing the QLX-I. We're going to data science. We're going into Python. We're going to be doing Numpy. And Numpy basically means probably what you think it is. It means numeric Python. So we're going to be doing numerals. And what I love about Numpy, it is the basis foundation for all of the big awesome packages that come through. Basically, without Numpy, you can't do pandas. Without pandas, you can't do matplotlib. Without that, you can't do scikit-learn, which is kind of the data science aspect of it. And it all starts with being very OCD. That's exactly what NumPys are. Putting everything in little categories and little buckets, and a really easy way to do it. So I'm just going to bring up 0, 1, NumPy. That's what we're bringing up here. And now the first thing I do show up here is, just as an example, is I did want to show you, and I also wanted to show my other class, the use of a program called Poetry. And what Poetry allows you to do is, right now, what I would love for QLX to do as a company is I would love for us to be able to build our own Python packages. And what Poetry allows you to do is to do that very easily. So as we're getting into NumPy and about to use those packages that build on top of each other, I wanted to kind of show that this Poetry is basically kind of an application that you can load, install, and you can create your own packages. Really basic ones. Just like, for example, my example was I was going to create a package called Gary. So it would just have my name and say, hello world. But then when I started building it, I started getting errors because there's Gary Python package. And it's basically about, there's Gary PyPy. Basically, it's a package for galactic astronomy, especially gravitational dynamics. So I couldn't create the package because it already existed. I think right now it's basically been shut down because it's been moved to another package, but that name is taken. And what I wanted to show in this very first example when you're looking here is how you could create your own packages using Poetry. And Poetry comes with tools that basically allows you to, it also allows you to be able to create inheritance. So if I create a package that needs pandas or Numpy or those things, it actually builds that inheritance in there so you don't have to do all that manual stuff. Again, this is purely, as I say right here, optional. But the goal is it's a tool for dependency management, packaging in Python. Super easy, super way to create it. And I give an example here when we do the Poetry so you can basically, develop a package, build one, publish it. Then you publish it on the test Python package one because you have to make sure it works and people can download it. And then you basically can publish it to the production Python package, which is what we call PyPy that's there. And we'll show that in a second. And then you can track as there's many variations and versions of that. So one of the things I always was trying to push is if we built something within SaaS, like a customer lifetime value package or some kind of thing that anti-money laundering or one of those things, basically you could build like just a basic framework for that, publish it, and then they have to buy a license to make the other pieces work. So, but it gets you into the community so people can start using you. And how to install it, super simple. You basically just go to command prompt, you type in pip, which is your Python install package, install Poetry, and then basically, if you're Windows, whoops, let me bring it back. Then you basically bring it back for, I have an installation for Linux, and then I have an installation for Windows. And then basically you look for the version. Then what we're going to do is we can go into, I can create a directory for my new package. And what does this mean, a package? I'm just going to create a directory and save all my .py files in there. All those files should call each other, and basically it's going to compress all of those that directory together to create that package, create like a little file structure. You can see here that it's created as I build this, and this is a fake one called Flake 8 Markdown, just a really basic one. Creates that directory, gets in a init.py that you need, then basically it has a little test package to be able to do some basic checks, and then it creates this file, which is the most important one, called a TOML file. It's like a markup language file that basically allows you to say, okay, what's the version, who's the author of this, what's it the Python is dependent on, what PyTest, which is basically the test development thing, is it being pushed to, and those kind of things, and what kind of APIs that you're using for. And you can update it, put new README details, homepage, keywords for search, and all that stuff. That's what that TOML file is. Then basically, again, I'm just going to show you in the notebook. We're not going to do anything here, but I'm basically, once you've created this little, you initialize and say create Poetry new Flake Markdown. Then once you're ready and got all your files ready, you just say a Poetry build from that location. Then you're basically going to push it to your test py, which is here, which is basically a test py repository. If I go click there, test py is just like PyPy, except it is a test. So, dev is local, test is here, and then production is here. This is PyPy. So what you're doing there is you're just basically building up. You have to register to do that. There's no cost. And then basically you set up the repository, and then you publish that to test PyPy, and just make sure the package looks good and works as intended, and then you can query it and you can install it version, doing an environment. And how you would install it is basically you would wipe out your directory, or make a backup, obviously. Then you just do pip install like it's a real package, but then you point it to this test py location to install it. Now, once you're ready to go big time with your package that you've created that does whatever it does, you can actually the next thing all you have to do is go Poetry publish, and it goes to the production. But you have to make sure that you've created a PyPy account, which is the production one. And then there you go. So I just wanted to put that out there to show you it's not that hard. And that's why the open source community with Python is just really blowing up and still doing very well after all these years, because it's so easy to create your own little tools. And if you do publish something and someone says, hey, I published something like that already, you will be notified. And then you can modify, or you could join forces together, be part of the community. So that's what's really nice about it. So that was poetry. I wanted to bring that up so you can kind of see that, and just to show you how easy it is to be able to publish free and create some stuff. And I think that that's something we really need to create from an intellectual property perspective for QLX. Now, let's get into NumPy. So Python NumPy is a Python package which stands for numerical Python. So it's basically a core library for scientific computing. It basically is the container that keeps all the numbers, all of the digits in a very nice, easy peasy way to be able to call things without having to create an array all the time or a list or those things. You can actually create an object with all these details in it and be able to reference those. And why you would need this is specifically for animations or for GPS coordinates. You know, when I was working for the SpaceX company, look at it, and I remember when I first taught this class was right before the SpaceX launch that we were all waiting to be able to watch, and then it got postponed to Saturday. The goal for this is being able to put all those GPS coordinates, which is a lot of numbers, in a very easy way that doesn't take up a lot of RAM or memory, and then it's easy to reference and be able to bring into. So that's what we want to do. Now, to install NumPy, you have to do pip install NumPy, which is package install Python install package NumPy, and this is how you would basically run it. So now that you've installed it, and how you would install it, just to make sure, just to show you I'm not, no tricks up my sleeve here, I'm just going to go pip install NumPy, and then basically it says it's already satisfied. If you've already installed Anaconda, which we did on the first day, NumPy is usually part of the basic packages. If you didn't install Anaconda, you do have to install it sometimes, because Anaconda kind of has kind of a foundation. But if we wanted to be able to say what version of NumPy it works, you basically just say import NumPy to be able to use it, and we're going to be talking about there's a standard for that and then the version that we have. Note, here's one problem with Python. It is an open source community that people are contributing to all the time. Things get deprecated on a daily basis. So sometimes when you're using NumPy or be able to play around with it, some function might disappear. They might rename a function. So what you'll see is there's a lot of change. And one of the things I wanted to bring up here is once you've installed NumPy and you've imported it, you can actually go through all of the arguments and all the options that are here that are available for this version, which is 1.18.4. You can pretty much do that with all packages. I've had to do that quite a lot when I was doing some of my other stuff that I get into, because some things get deprecated. If you start getting an error and you're like, man, I just know this is a stupid error, it may be a stupid error because you're using a flag or you saw something on Google that worked, you put it in the notebook, it didn't work because that flag or that argument they don't use it anymore, and they didn't tell anybody. So, but they've changed it, and it's in the documentation. So anyway, I just want to let you know that that's a common thing that happens with. That's a common thing that happens within Python packages and as we go through. Now, when you're going to use NumPy, this is common. You always use import NumPy, and you always call it NP. It's just a standard. You can call it whatever you want, but for most of the community, they use NP. And as I was saying there, you can look for the functions here for, just hitting tab. All I'm doing is type in NP here, and then I'm tapping the tab button. And then if I wanted to get questions, all I got to do, I got to make sure I run it. Sorry. And then run a tab. There we go. So you can see all the documentation. Or if I wanted to be able to see all the help, you can just put the question mark, and then bam, you got tons of help that's here. A little bit too much help for my case. So, and I want to close this down so I don't have so much help. Let me get this over here. If not, I know you can close it somewhere. Let's just go here. Okay, and then let's bring this down. There used to be an X button here, but I'm doing there we go. And so we're doing this. So there we go. So we have the NumPy. So now let's get into the basics of NumPy, which you're like, wow, cool, only one notebook. Let me tell you something. This one-page notebook is a humdinger. It is long and a lot of detail. So we're just going to try to hit on a lot of that. I've included a Numpy video tutorial. So basically, you know, if you miss something I'm saying, or you don't like what I'm saying, or you're just bored out of your mind, this video really hits all the same things I'm talking about here. I didn't create it. This is one of the ones that's out there and available. That's the beauty of Python too. Technically, you don't have to take training. There's so much stuff that's out there. But anyway, so NumPy's main objective, and let me just make this a little bigger so everybody can see. NumPy's main objective is to create a multidimensional array, a homogeneous multidimensional array. It's a table of elements, usually numbers, all of the same type, indexed by a tuple or of non-negatives, and NumPy dimensions are called axes. Now, all we're saying there is we just want to be able to collect data in a nice, easy, referenceable way. That's all the NumPy is doing, and that's its only function. So without all those technical words, that's what we're doing. So basically we're creating, and you can always see that we're creating NumPy values because we're using brackets. And we're going to get into that and how those brackets work. And you can see that there's a lot of variations of using NumPy. So there's a NumPy array class called NdArray. NdArray is known by being able to create an array on the fly. It's basically kind of, and we'll get into that. So I do want to let you know that as we're talking about this, NdArray allows you to create different dimensions, different shapes. Shapes is basically determining how many items is in your array, you know, how many dimensions, how deep is it, how many numbers are in there, the size of the elements of the array, that's what size is. What is the type? Is it an integer? Is it a float? That's what dtype is. The item size too, if you want to know if it's 64-bit or one of those things, and you actually, if you want to be able to print out the actual elements of the array, that's why ndarray.data comes in. So let's give some examples. So I've imported it NumPy as NP. No, this sounds really kind of boring, but everything's based off of this. You create a variable called A. I'm going to create a range, which basically what I want to do is I want to create I want to go from 0 to 15, 0 to 14. Remember, when you're starting to create numbers, it always starts at 0 and goes up, just like the elevators in the rest of the world except in America. And then what we want to be able to do is I'm going to create a range. So I'm going to start counting numbers, and then I'm going to break it up into 3. Shape it into 3 with 5 numbers each inside of it. Why is this necessary? A lot of this times is for pixels, or being able to generate animations, or if you wanted to be able to create coordinates, exchanges for currency, those kind of things. So that's why NumPy is there. So basically I'm creating this, so it's 3 with 5 elements per each. Now just to print out this, all I got to do, I don't have to say print. All I got to do is say, and I'm just going to put it down, and all I got to do is type A, because it's a NumPy. Boom, it already prints it out. I can say the shape. Shape just means, okay, I have 3 axes with 5 elements in each. The dimensions I have is 2. I'm basically, and then basically the type is integer, and the item size is 8, and size is 15. That's the number of numbers and the elements that are in there. And the type of what is A? It's an NdArray. That's where we're building an array. And then basically you can modify it. Now we're going to create a new one called B, MP array with 6, 7, 8, which is creating that one little array. So I don't have to make it count it through. I'm just going to force an array in there, 6, 7, 8, and then I can print that array out. And then what does that be? It's basically an NdArray as well. So the other thing that we want to do is you can create an array from a regular Python list or tuple using the array function. So, which we've just done. We've created an array here, just adding numbers in. Boom, created it 2, 3, 4. Print out 2, 3, 4. There it is. What kind of type is this? Integer 64. Now what we can do is we can, on the fly, we can actually rename or create. We can change it up. So I'm actually going to call it B, call it MP array. Now I'm going to be adding floating numbers or decimals inside that. And then once it rewrites that and opens it up, then you can see that what type is it now. It's changed to a floating 64. You can also sometimes you can get a lot of errors sometimes with calling arrays with multiple arguments rather than providing a sequence as an argument. So as we're calling this, you can see this is non-keyword arguments because we're calling it NP array. That's wrong. If you wanted to be able to do this correctly, super simple. All you got to do is, because we're not building an array, we are, but we're building a Numpy array, and to be able to do that, you need to have those brackets around it. So that's the right way to be able to create that one. Arrays transform sequences into two-dimensional arrays, sequences of sequences into three-dimensional arrays, and so on. And we're going to start getting into those dimensions because those dimensions mean a lot when you look at this, and we'll kind of show how that looks as we go through this. So what we're doing here is we're basically we're creating an array called B. We basically have a decimal, and we have some decimals, and then we have some non-decimals in this. And as we create this array, so basically it has, and if I wanted to go, let's see, if I wanted to go, where's the one I wanted to see? There. So if I wanted to go shape, cool. So basically what we defined there is I've created this array. It basically has two in there, and then it basically has three items within that one. So if we wanted to print that one out, boom, there we go. You can also do explicitly created. You can actually define the type of array when you created it. So basically what we're saying is we are going to, we're creating the array, we're creating the brackets, but we're saying that the D type definitively is complex, which is where we're redefining the array as a complex one. We could even here, if we wanted to, we can call this integer 64. I don't think that would work. What is it, a float? What's a float that I could do? A float 64. And then I can do 64. Let's see here. Might give me an error. Oop, I need to put it in quotes. Sorry. There we go. So, and the reason I put it in float, well, I could call it in, it could have been an integer or those things, but it's actually creating a decimal point for me there. The other thing that we want to do is sometimes we want to create an array, but there's nothing in it, and maybe we just want to save, we just want to save numbers for the sake of saving numbers. And again, one of the things that I used to have to deal with quite a lot is being able to plot wreckage, trash that is in orbit. Around the Earth, especially around around the MEO, which is middle Earth orbit, and GEO, which is geosynchronous Earth orbit. And you're like, what? Why would you have to do that? Because there's so much. Every time a space launches, except for SpaceX, they're trying to keep the trash down. But in the Apollo launches and all those other, and the spaceship launches that happen with the Russian launches and the Chinese launches, every time they launch, they just throw away a booster, or a piece of paint falls off, or a blob of gas. I'm sorry, of gasoline or fuel just stays in orbit and is captured by Earth's gravitational pull, and then it starts to move around the Earth orbited. And by default, it can go up to 17,000 miles per hour. So all these little pieces of trash, if they collide into each other or collide into a satellite, they would create more trash and more of those things. And we'd have to trace those out on multiple dimensions. But to start defining that and start to plot them out, we would have to create these arrays to be able to, that would have empty spaces in them, so we can start saying, oh, I found this satellite, this is where I found this piece of trash, found this nail. And you probably remember just a couple of months ago that they were in the space station, and all of a sudden a hole got punctured into the ISS. And a lot of people were saying that it was deliberate and those things, but no, it was actually probably just like a screw. If a little bitty screw that's been coming off one of the spaceships or space shuttles or boosters, when it starts rotating, it goes like a bullet. 17,000 miles per hour is not slow, and it just ricochets through anything and tears it apart. And so we had to keep up with that. And that's what this is really nice about, is we can actually create an array and define it with zeros so we can use it at a later point. And what's great about that is it grabs that space and memory so you can actually allocate it and use it over and over. So what we're doing here is we're basically saying we're going to create an array of ones, and basically you can see here what we're doing here. We're actually going to say we're going to create two axes. We're going to have three I wouldn't say dimensions, but then 4 elements within those. So you can basically, and we're defining the type to be integer 16 as we're defining what's going to be in there. And so, and we're not doing zeros there, we're just doing ones. And sometimes you would do that as a default number that you'd want to be put in the array. So if you forget, it won't just be a 0, it would be a 1 that you can actually maybe add all of those things together. You can also do ones where basically you can do an empty one that says, okay, I just wanted to define this array and be able to put it in. And then that's basically an uninitialized array. You can create sequence of numbers, provides a range function that is analogous to basically Python built-in range. So basically what we're doing here is, what I want to be able to do is I want to be able to create, I want us to be able to go from 10 to 30, and I want to increment by 5. And that's what this arrange function is doing here. So I'm creating an array by starting at 10, going to 30, and I'm incrementing by 5 to get there. Once it hits 30, they'll stop. Then the other ones, when it says it, you can also create arrays. It will accept both integers and floating point numbers right away. So you can throw those things together, which is pretty nice. What we want to also do is you can also do something called line space. So you can actually, you can kind of put in elements to have some spacing in between those. So, so line space receives it as an argument the number of elements that we want instead of the step. So if we wanted to be able to go from 0 to 2, and we want to be able to increment to 9 numbers, then basically what we can do is it basically will, using line space, it will start incrementing up to be able to create those numbers, 9 numbers from 0 to 2. And yeah. So don't want to get into the sine, cosine thing, but you can kind of see there. So printing arrays, really easy to print array. All you got to do is actually type the word, once you define it, A, put a range, then you can just print it. Or you can basically just type, not a big deal, I can do the same thing. I can say I'm going to create an array of 6 numbers there, and basically can do the same thing. So if you just wanted to just have the numbers in there, super simple. There we go. And you can basically say we want to be able to create an array called B. We want it to have 2 numbers, but then we want to reshape it, which basically means I'm going to have 12 numbers in it, but I want to break it down into, I want it to have 4 elements, 3 elements, and I want to break it down by different axes as I go through this. And then C, of course, we can have 24 numbers, and I want to reshape it in a 3-dimensional array. And how does that a 3-dimensional array look? What we're doing here is we're basically creating and you don't really see it, but you're creating you're creating 2 axes with 4 numbers in, but then there's basically, you're seeing that there is another dimension. And we're going to get more into the dimensions a little bit later as you go through this. The other thing too, which is nice about Numpy, is you can create lots of numbers, trillions, zillions of numbers. What's nice about it, it does create an object to be able to do that, but it doesn't have to keep incrementing up to store that up into memory. So when you do create a Numpy array, let's say it's 10,000 numbers, it will only give you the first 3 and the last 3, and just have ... to show you, hey, I've allocated, it's ready to go, but you don't have to print it out. Don't do what I did. I remember when I was getting ready for one of the classes, I actually printed this one out. So basically I'm creating a Numpy array that's 10,000, and I reshaped it by basically saying I wanted to be able to have 100 numbers per 100 axes. And this is 9 pages of print, by the way. So I killed 9 pages of not my paper. Unfortunately, it was my girlfriend's printer, so I destroyed her ink and her thing, but just totally forgot. But and what we're doing there is we're actually, why did it choose to print that without just doing the top 3 and top? I forced it to print out all of the numbers, and that's what this function here is. MP set print option threshold sys max, and then basically when you do that, it actually will create and allocate and print all of those, by the way. Here's some basic operations of math. You know, it's super simple to be able to go through this. We're going to create an A, we're going to create a B. What's cool about this is we can say, okay, we're going to create, this is our array there that we define in, and then basically we're going to create we're going to create one called B that basically has 4 numbers in it from 0 to 4. And then we can actually start subtracting numbers from that. So we can say C equals A minus B, and then print out C. And what does that do? So when we do that, oh, let me allocate it, and then we go this. So what you're going to see is, because we have these numbers in here, it's basically going to subtract 0 from 20, which is 20. It's going to subtract 1 from 30, 29, and then of course 2 from 40, 38, and 3 from 50, which is 47. So allows you to subtract an entire array together against each other, which is kind of cool. And then basically what you can do also is you can do a square if you wanted to, so b squared. So what I could do is take 0 times 0 is 0, 1 times 1 is 1, 2 times 2 is 2, and 3 times 3 is 9. So you can write really quickly in the array, be able to create something. And of course there's, sine, cosine. I kind of created this little graphic to kind of see what it is. You can also basically kind of assess your array to see, is the numbers that are in there, is it less than 35? And you can say yes it is as we go through this. What is that? Is there anything else we're saying here? So we're basically creating two arrays here, basically two elements, two axes, and then B going through this, and then basically we can multiply those together to be able to by element. By the way, that's the element-wise product. Is there anything we want to be able to say? Now, if we wanted to go a little faster for this, we can actually do the same thing, where instead of having to type and be able to create this whole thing, we can also do something called an @ sign. So the @ sign allows you to do a matrix product versus all of these together to create the output of them together. You can also, to do this means multiplication from one array to another, and then A dot B allows you to do the exact same thing, all this array multiplied to all of this array as well, each one individually by its indexing. Some of the operations, plus equals and times equals, act in place to modify an existing array rather than to create a new one. So basically what we're doing here is we're creating a random number, default, kind of creating a random generator. Then basically we're going to create an array of ones that basically has 2 with 3 elements, and it's going to be integer. And then basically we're going to create a B, which is a random generator. And then what we want to do is we want to multiply that towards this. And so what we can do, let me just run that one. So you can see here that this ones, and then basically multiplying it towards the random generator for this, it multiplies it all out. And you can do the same thing for, you can do a plus. So it acts as a way to modify an existing array instead of creating one. So you can modify your array. Now what you can't do, and I think we're going to be showing this next, is so if you have two different types, float versus integers and those kind of things, it doesn't automatically convert the integer type. It will give you an error right away and say cannot add output from d-type from float to integer because it has to be same kind. So we'll give you errors there. We're creating an array here with ones. It's going to be integer 32. Then we're basically going to create a line space where we're going to be creating starting with 0 and creating multiple numbers. Then what is the d-type that we're going to be doing there? It's float 64. And then you can start adding those numbers together to create another variable, another array, I'm sorry. So the new array C is A plus B that we've created. So now it's a new array. What is that array type? It's float 64. You can do exponential addition as well. So we're going to create a D, and then basically you've created that, and then what's the D name? It gets a type. So the next thing what we want to do is urinary operation. Urinary, right? And then basically all that means is, it sounds like a crazy word, or it sounds like a urinary tract infection. None of that. It's not a UTI. All that it means is it's an operation with one operand. You're just being able to pass one thing into it, a single input. That's simply, they could just say single input, but instead they want to go to the Latin and use urinary to make you think that you have a UTI. Anyway, so what we're doing here is we're creating a variable called A. We're creating a random. We're going through here and we're actually creating multiple, we're creating an array like we were before. But we can do some really cool functions where we're going to just do one input. So now I can do a sum of everything that's in that array. I can do what's the minimum in that array. So A.min for that array, it kind of points it out. What's the max? So really nice features from Numpy that allows us to be able to do that. The operations apply to the array as though it were a list of numbers, regardless of its shape. Specifying the axis parameter, you can actually apply an operation along with the specified axis. So what I can do here is, now I've created this array of 12 numbers. I'm reshaping it so it can have 3 axes with 4 elements each. Now what I want to do is I basically want to do a sum with the axis of 0. So what is it doing there? It's taking this first axis, which is here, and it's adding all those numbers together. So which would be 12, 15, 8, sum of each column. Right. So basically what it's doing is it's summarizing each of the columns as it goes through here. So if I do this and then go through here, and then basically it's adding these two together. So 4 and 8 is 12, this is 15, this is 18, this is 21. As you can see through that's what sum axis 1. And we can also do the minimum of each row. So if we wanted to be able to bring up and do axis 1, what we can see here is 0, 4, 8. So it's only doing the axis 1 that's there. And if we wanted to be able to do a cumulative sum around each row, you can basically do the exact same thing and point it to axis 1. So it would be you're basically 0, 1, 2, 3, 0, 4. Yes, being able to add that through. Okay, we're almost done with this. Just trying to get through all of these. It's a pretty quick. You can kind of get where we're going with all this stuff. NumPy allows you to create really awesome, big, large number arrays. All the number arrays are needed for all the other functions that are happening within Python. So you can do universal functions where you can do an arrange, then exponential. You can do a square root. Then basically you can create another array here, and then you can add the two, the square b, the exponential square root of that one to c, and be able to create an array from that. You can also do slicing, like what we were doing before with lists and those kind of slicings, iterating. So you can go straight into an array, only be able to use a piece of it to be able to do certain things. So if we're creating an arrange of 10, and then we're going to not square qubit, then basically you can go through and do that as you go through. Now what we want to be able to do is I just want to pull out the index of the 2, which is right here, number 8, and I can just use that as a variable if I wanted to. Or I can bring out a range, 2 to 5, so 8, 27, 64. That's 2, that's 0, 1, 2, and then 3, 4, 5. You can see there. And then if we wanted to be able to create from start position 6, and set every element to second element to 1000. So what we want to be able to do is read this all the way through, and we want to be able to print out from 6, and we want every second element up until we get to not greater than 1000 if it exists in the array, and that's what we're doing here. We're basically saying, okay, bringing it out and then going through. Whoop, make sure that one, and then go this one. Oh, I've totally screwed it up. Go here, cool, then go here. And remember too, when you set these up, as we're defining these, note too that is if you've run them in a different order, it will reset that array and change it up. Now what you can't do with an array is, once I've created an array, I can't just go in and change one number. You have to change the whole thing or delete the whole thing. You can't just go and change it like a list or something like that. So as we're iterating through to be able to create these things, you can see you can basically have multidimensional arrays, can have one index per axis. These indexes are given in a tuple separated by commas. So I'm creating a function here. I'm being able to multiply these things together, and from the functions I'm being able to create something which basically I'm going to iterate through to be able to create this array. Whoop, and let me define it and go through. Remember, you have to focus. And then what we're going to do is we want to be able to grab B out of the array, which would be 2, 3, which is 23. And so what you'd have there is basically what we're going to do is we are going to the second axes with 0, 1, 2, and you're getting to the 0, 1, 2, 3 number that's there. And each row in the second column, you can see that. You can see it allows you to slice it and bring it up, and we can do bring in each column for the second row. And if you want to go backwards, so instead of reading forwards, you want to read backwards, you just do like we did before in our former class, go in -1 and go backwards. So it starts reading it from backwards to frontwards, 43, 42, 41, 40. That's what it's doing. And of course, have an attribute called shape that returns a tuple with each index showing the number of corresponding elements. We've already talked about that, so that's what shape is. We built this array. So what is the shape of this array? We have basically 2 axes. We have 4 elements each as we go through that. And then basically if we create this array, which is C, and we look at the shape here, we're showing a 3-dimensional array, 2 stacked to a D array. So what we have here is we have multiple axes, and we have the different elements that are in that. And that's not really a good example because it really doesn't show what dimensions can look like and that kind of thing. And you can also see a range. So if we wanted to be able to grab everything that is in that array starting from 1, you can basically just go 1 and then ... to bring it in, or you can do the same thing with a range. I don't ever use that one that much because it's too many just to get it, and there's a little shortcut you can do a little bit later. For row and B, be able to print this. So we're basically printing out the rows that we're creating and doing that, and of course this. The last thing is, now what we want to do is we've created a range of numbers. Now we want to reshape it and create different kind of arrays within that. We want to create different axes, number of dimensions. We want to reshape it. Shape manipulation is what we're doing. So if we create this array called A with random numbers, and there it is, defined by A, and we shape it, boom. It's just basically, that means 3 axes, 4 elements each. Okay, that's good. But now that we want to kind of change it, there's something called an array ravel. And what ravel means is I'm going to flatten this. I'm going to get rid of the axes, only have 1, and so everything's unraveled and put into one big array. And a ravel just means it's flattened. That's what it means when you put it together. We can also do a reshape where we can take the same numbers for A. Remember, it's just numbers being modified and changed. Now what I want to do is I want to create 6 axes with 2 elements each. That's what reshape does and allows us to do the exact same thing. And if we want to transpose the numbers to completely go from the one direction to the other one, what we can do is just go A with a capital T. And that you're going to see that show up many, many times as we go forward with Numpy's, Matplotlib, and some of the other ones as well. And so to go through that. And then you can actually reshape if you want to transpose it, which means if I had 3 axes with 4 elements each and I want to transpose it, now you can say 4 axes with 3 elements each. You can just switch it. So I created this little cheat sheet, this little image file, something easy to print out if you wanted to or be able to see. It tries to show you the examples of reshaping, ravel, 3D arrays, 2D arrays, flattening, stacking, which basically takes an ravel and then pushing it to the side. And again, this is just ways for you to understand where the numbers are and how you're keeping it and how you can reference those. So I put them here for the reshaping these, so you can use that. Then you can also say, we talk about how the reshaping works, where basically it's taking something that's already kind of shaped up by, 2 axes with 3 things across, and then we're going to just basically reorder it very easily. You can stack together with different arrays. So if I'm going to create a, you can stack it with different, and I have a cheat sheet on this on what floor means and some of those. So we're just creating different arrays around that. And there's a horizontal stack, there's a vertical stack. It just depends on how you want to kind of put it out and go through that. And I created a little cheat sheet here to kind of show you where stacking and horizontal stacking and how that would work. I don't think we have any exercises or examples that force you to do this, by the way. So just something to be able to put in there. You can also do something called horizontal split. You can split an array along its horizontal axis, which is what they're doing here. And okay, now we're getting to the end. And this is where our SAS skills come into play. Something called copies and views, which we both know if you've ever worked with SAS coding language before. Now I have this massive array. I have all these numbers just right. And remember, the reason you'd want these numbers in there to be locked and loaded is for currency exchange or GPS locations that can't change, but I just need to reference those numbers quickly. But maybe I do want to do a modification. Maybe I do want to edit or change. That's where we can do a copy or a view. A copy is basically a complete copy of the data, and you can reference it and change it and delete it and do whatever you want. A view is basically using the one, it's just like a SAS view. I'm actually just going to make a symbolic copy of it, and I can reference it and do indexing and slicing and change things up, but the original does not get modified. So here's one where we're going to be basically saying, we're not doing a copy at all. We're basically going to say we're creating this array called A, and then we're going to say B equals A. Now B is A, and so I can actually start referencing B just like I do A. So so we're just saying no new object is created. A and B are two names for the same object. Remember, everything in Python is objects. When you create it, it's an object can be referenced. So B is A is B, you are me, I am you, we are love. Very meta, if you will. Python passes mutable objects as reference, so function calls make no copy. So if I want to create a function here, be able to create this and be able to, I can actually say ID is a unique identifier for that object, and then basically I can actually reference that object as I go through. There's a view, or what they call a shallow copy. So we used to call them SAS views. What they call them is view or shallow copy, which basically means you're being able to modify the data without actually touching the real thing. So if I create C equals a view, which is that data we just built, let me just make sure I created that data. Cool. And then let me run the function and make sure the function works with that one. Cool. And then what I'm going to say is C is A. I'm creating a C is A dot view. C is A. No, it's not. It's a view. It's not the real thing. It's basically it's not a copy either. It's just pointing to C so you can kind of reference it. But C technically doesn't really even exist. It's just a view of that. So basically you can say is C is a view of the data owned by A, C base is A, and that's correct. What it's basically telling you is C, where is it coming from? What is its stem? And the stem is A. And then basically the C flags, does it own the data? No, it doesn't, because it's a view. And then we can actually reshape. So if we did C reshape 2.6, A shape will not change. So for example, let me just do this. I'm going to go, so okay, so we're taking A that's already kind of defined, and if we, you can see that we've defined C now as a view into 2 and 6. So basically 2 axes with 6 elements each. With A shape now, it still stays the same. So just to kind of point it out, so if we do some configuration and we do some changes within C, A also changes, by the way, too. So you can see here that what we're doing is we're going to say, I want to change this C to 1234. It's actually going to impact A as well, because it is a view. Let's see, almost to the end. Slice an array returns a view of it. So basically what we want to do is spaces added for clarity. What we want to do is go through this range. We actually want to go to this one and change it to 10 is a view of S, not the difference between S10. So basically what we're doing is S equals A, and we're just taking a slice of that array, and then basically we want to be able to print out those. But you can see that A is still the same, and if we wanted to go see S, cool. So basically you can see that we've basically taken A and redefined all the numbers inside S as tens. A deep copy is exactly what a deep copy is. It's exact copy for copy, one array to another array. So D is a copy, D is A, as we go through this, correct. It is actually a copy. They're not the same. That you can go off and modify and change and delete. Remember though, every time you start making these copies, you're taking up memory. When you do a view, you're not really taking up a lot of memory. You're just using one array to be able to do that. So just remember, the bigger the numbers are, the more it takes out, the more copies you make, the more system memory you might be taking up. So D base is A, that's correct. It's saying it's false because it's not. And then basically you can be able to create, go through the range to be able to say, okay, now what I want to do is I want to change the number that's at this location to 999. Now I'm going to print out A. I don't see 999, but what if I wanted to print out B? Boom, you can see the 999 changed, even though, because they're a copy. And then basically going through the range and being able to delete that array. Okay, so with that being said, is in a real world example, okay, that's not where I wanted to go. Go back. And that's it. That is really all I wanted to kind of cover. I know that was a lot of me talking and showing you exercises and examples, but let me just say we do have some examples, and this is where I'm going to try to wake up Scott after talking so crazily. And I was going to see, Scott, if you wouldn't mind walking through your exercises. So exercises 9, Module 9, practice exercises, is a HackerRank problem. And basically what they're asking for is they want us to create, the task is you're given a space-separated list of numbers. Your task is to create a reverse NumPy array with the element type float, which is that. Did you want to talk about that, Scott? Are you available, or did I put you? Are you
No,
dead?
I'm still here.
Yeah. So I'm going to bring up yours. Give me 1 second, my friend. And that way nobody has to do them, because Scott, because he's awesome, did them for you. So you don't have to do anything.
Scott is bored.
Yeah. Well, that's my number one goal, is trying to make people a little bored. Yeah, here we go. I'm bringing up yours now. So here we go. So the task is a space-separated list of numbers, and here's what you did. Explain what you did.
So I took the list as a input, or the input as a list.
Yep.
And split it so that it's however many elements for each item.
Yep.
And then pass that list straight to the print statement, but within it you use the create the NumPy array, and then you use the slicing and indexing part functions of the array or the list to reverse the order, and then I pushed it out as a float.
Nice. Yeah, and so I was going to ask, and it also asks, and you did it. Yeah, type as float. Yeah, so perfect. And when you submitted this, did you submit it within HackerRank? I'm going to see if I'm.
No, I did I do that one or not? I'm not sure.
Well, you know what's funny is
the one. The reason I didn't is they insisted that you develop this array. I couldn't get that code out of there.
Yeah, I know, that sucks. Yeah, that's the thing that's.
I just wrote it.
Yeah, that's good. That's fine. It's a pain in the ass. It's like they're forcing you to think, not be creative. You must do it this way, or you suck. I get it.
Yeah, I suck often in HackerRank.
Right. Yeah. You want to do this now? I think we only have 2, right? We only have 2 examples. Right. So what about the second one? So the second one is basically the task is given the coefficient. Oh, this is so mathematical. The coefficients of polynomial p. Your task is to find the values of p at point x. Be glad Scott did this for everybody. Do you want to explain it? What you did?
Same thing. You're inputting 2 things. One is a list of coefficients. That's in B list.
Yep.
I did a map to make it float because you could pass it to anything numeric.
Yep.
Then I put in the value that you're going to be testing the intercept value.
Yep.
And that was just an integer. Then you this time I tried to get clever and
nice.
Not create an array. So the bracket from NP array takes basically the same thing. It takes the list that I inputted, converts it to a NumPy array, and it passes that 2 values, the NumPy array and the intercept, to the function polyval, and it comes back with a response.
Nice. And let me ask you, do you like it that it reminds me of when I first started learning SAS, that you can do these little clever one-line pieces of code? Do you like that about Python, that you can kind of, it depends on how you can, as long as you understand the logic.
It depends on my mood of the day. If I'm like, I want to write the densest code ever,
yeah, I'll
write this. If it's one where I got to fix this,
yeah,
I tend to break things apart. But I do like being able to write code that at least even makes me scratch my own head.